Welcome to the show, Khan Academy. My name is Max.
And I'm Ashton.
And we're Team Quantum Blackboard.
So let's terminate some ignorance.
Today we're going to be talking about a very controversial subject, physics. But not just physics in total. We're going to be talking about the four fundamental forces. Let's get started with the weakest, gravity. Gravity plays a massive part in shaping the universe as we know it. It is the force that keeps me from floating into the space above, prevents things from escaping a black hole, and forces the Earth to orbit the sun. Most of us know that much about gravity, so let's dig a little bit deeper. Another good example of gravity's work is this man doing a Turkish get-up. Gravity is the thing that makes the 100-pound weight heavy, and is the force that governs how much damage he will deal to himself if he lets go of the weight. Gravity is felt between all objects in the universe. Even massless objects like light are affected by gravity. Most look towards Albert Einstein's theory of gravity to explain this phenomenon. The theory is that gravity happens when space is curved or warped around a mass. Since everything has mass, with the exception of massless objects like photons, everything to some extent has gravity. This diagram depicts Albert Einstein's theory the best. Mass creates a dip in space. This dip acts like a funnel, and things can fall into the funnel. The more mass something has, the more gravity it has, because it warps space more. On the surface of a planet with more mass, the object is heavier than a planet with less mass, due to the more mass equals more gravity, and more gravity equals more mass. If a cannonball is moving fast enough, it can orbit around a planet. This is because the cannonball falls into the funnel that the planet creates. This causes the cannonball's movement to curve toward the planet. But the cannonball is moving too fast to miss, and misses the planet. The pull of gravity again curves the cannonball's movement, and again the cannonball misses the object. This happens over and over. Extensive research has led for us to believe that Albert Einstein's theory is correct.
Now that we've talked about gravity, let's talk about the next strongest fundamental force. That force is called weak nuclear force. This force governs all matter in the universe. Weak force, or weak interaction, plays a critical role in nuclear decay, unlike all the other forces that play an important role in holding things together. Weak force only functions at the subatomic level and is responsible for much of natural radiation. Weak force's job is to change protons to neutrons and vice versa. This process is called beta decay. The force achieves this by changing the flavor of quarks. There are 6 types of quarks: up quark, down quark, strange quark, charmed quark, top quark, and bottom quark. 2 up quarks and 1 down quark make up protons, and 1 up quark and 2 down quarks make up a neutron. Weak force changes a up quark to a down quark, and the other way around. This results in the change of a neutron to a proton, or a proton to a neutron. Weak force, like the most of the fundamental forces, has force carriers. Its force carriers are called the W and Z bosons, and their job is to change the quark's flavor. W bosons are electrically charged. They can either be found as a negative W or a positive W boson. On the other hand, Z bosons carry a weak neutral charge and are very hard to detect. Weak force has one more trick up its sleeve. It can also change the quark's type through a process called electron capture. This happens when the electron in the orbit closest to the nucleus falls into the parent nucleus. The nucleus captures the electron by producing a daughter nucleus and a neutrino, which is another particle. It's a lepton. The atomic number is reduced by 1, but the total number of neutrons and protons stay the same. Weak interaction shapes the universe by changing elements and allowing the sun to shine. Let's talk about the troublemaker that makes strong force hold atoms together, makes electrons orbit nuclei, and who makes it possible for electrical current to flow through wire. Yeah, we're talking about the electromagnetic force. Electromagnetic force affects all charged particles. This electromagnetic force explains why many of the phenomena mankind is familiar with happens, like the aurora borealis and this chain of magnets. Magic? No. Electromagnetic force? Yes. electromagnetism, most things have charges. There's a positive and a negative. Charges that are opposite attract, and on the other hand, like charges repel. There is also a neutral charge that is equally positive and negative. When a neutrally charged object, like a balloon, rubs up against another natural object, like a wall, referring to the famous balloon experiment that you surely done in your childhood, negatively charged electrons move into one of the two objects. This makes one object positively charged and the other negatively charged, and they stick to each other. Now we know a little bit about the structure of electromagnetism. Let's see how electromagnetism works and how it shapes the universe. On the subatomic scale, the battle between protons repelling against each other due to all of them being positively charged and a strong force holding the atom together rages on. Since the electrons are negatively charged and the protons are positively charged, they extract and the electrons orbiting the nucleus, similar to how the Earth orbits the Sun. But instead of gravity pulling together, there's electromagnetic force. In the early 19th century, a man by the name of Michael Faraday showed that a coil of wire, when an electrical current is applied, has a magnetic field, and that when placed against another coil, creates a current in that coil. This is called an electromagnetic field. Let's get even crazier by bringing in quantum electrodynamics. In Einstein's investigation into the photoelectric effect, in which light can dislodge electrons in a piece of metal, came the discovery that electromagnetic radiation, EMR, can behave as a particle and a wave, similar to photons, wave-particle duality. Electrons inside of an atom can gain energy by absorbing a photon and lose energy by releasing one. EMR is explained in this context as an emission of photons when electrons experience a lower in energy. According to quantum theory, all fundamental forces need to be a force carrier, so to explain the force in which a wave compatible with quantum theory, they created quantum electrodynamics. Electromagnetism's force carriers are virtual photons that pop in and out of existence for only a short amount of time during interactions between charged particles.
To conclude our speech about the four fundamental forces, let's talk about strong force. Strong force is the force that keeps atoms' nucleus together, but strong force's range is only limited to 10 to the negative 15th meter and 8 to 10 to the negative 18th meter. But don't get me wrong, strong force is strong. It's stronger than electromagnetic repulsion. Due to electromagnetism, then the nucleus of the atom is unstable due to the fact that the protons repel each other. If it was not for a strong force, everything would be a jumble of particles. Strong force's carrier particle is called a gluon. There are eight different types of gluons. These mighty engineers hold corks and nucleuses together like glue on paper.